Hi, my name is Todd Morehouse. I'm a PhD student under Dr. Rulin Joe at the University of Massachusetts Dartmouth. Today, I'm going to go over modulation classification, convolutional neural networks, and give an example in MATLAB and show how we can modify this just to get a better understanding of how it works. So shown here is a typical neural network. If you haven't seen one before, on the left here we have two inputs. Uh, and we're going to map this to the output here on the right, which is just a single output. In the middle, we have we have a number of layers called the hidden layers. We don't see these, but they essentially just give us some complex mapping between these inputs and outputs. By using machine learning, we can learn whatever mapping gives us our desired output so that we have some function. So we have our known output given the input data, and we just want to find some. We're going to train this so that way it basically performs whatever function that gives us this mapping. Convolutional neural networks, in particular, make use of feature extraction before these neural networks. So we have our input data, and then we feed that to a convolutional feature extraction, which will also be machine learned. And then we have some neural network output activation that's going to transform these features into some desired result. These networks can exist with any number of inputs or outputs. In this case, we have up to n results here. We can have as many as we want. And we can also stack each of these blocks in different ways to make complex architectures. So in this case, on the one in the bottom here, we extract features from this input data. We generate some feature matrix. That feature matrix is given to this output activation that gives us our first result. We also feed that first feature matrix back into another feature extraction, as well as the first result to get our second result. So in this case, we could have two different results as well as one that relies on some more granular features. Some of the advantages of CNNs include their feature extraction ability. They have, since they have feature extraction built in, this is a great advantage over some other networks such as SVMs or LSTMs, which you would generally implement a feature extraction algorithm to pre-process the data before you input them into a CNN, the classifier or whatever you're going to use. This feature extraction has been so successful that you might even find hybrid models between CNN LSTMs or CNN SVMs, where you'll use a CNN for feature extraction and then feed the results into an SVM for, say, classification, or LSTM for classification or regression or sequence to sequence mapping. This feature extraction also makes CNNs great at handling large data. The so this feature extraction we train the feature extractor to only extract the features that are relevant for our application and discard everything else. So basically, we're removing data that isn't relevant or compressing this data. So in image processing or video processing, where we might be dealing with very large amounts of data, this is very useful. So that way we can do things in real time. And even in signal processing, where video might be limited to 60 frames or 100 frames per second, you'll be running in signal processing, you might be running this much quicker. The complexity of CNNs can be easily scaled to higher up to higher complexity in both the machine learning sense and the sense of how complex the architecture is. In the machine learning sense, we can have a more complex mapping between the input and the output. And we can also create some very complex architectures to tackle very complex problems. And the last point is that they're very popular. You'll find no end of resources for working with CNNs between MATLAB examples, or if you want to work in Python, TensorFlow or Theanos. You'll find plenty of examples there and support. as well as any support forums like Stack Exchange. You can find plenty of people there who are also working on similar problems or using CNNs. So this diagram shows, this diagram from Towards Data Science shows kind of the architecture of a CNN. I highly recommend reading their articles on this. I've linked them in the references of this PowerPoint. They're great resources for seeing how CNNs work. In this case, we want to classify handwritten digits by whatever digit they represent. So on the input here is the handwritten digit 2. And so the first thing that we do here is we use convolution to extract features from this. So here we have our feature matrix as the output of this convolution layer. And then we refine these features through maybe some max pooling or activation or batch normalization. And we can repeat this process of convolution and feature refinement to extract more granular features the more layers we put this through. Additionally, we also increase complexity there. Finally, these features are flattened. So we just take the matrices and turn them into a vector. So that way they can be fed into a fully connected layer. This will produce logits that we can then use for classification or regression. The convolution layer here is really the heart of what makes a CNN the CNN. This is really what's performing the feature extraction. This work, what we do is we define what's called the filter or the kernel, and this is going to be some m by n size here. So in this case, it's a 3 by 3 size filter in this graphic, and this filter will be slid over the input, and we multiply every pixel or every element of the input by the weight of the filter for that dimension. And then we might add some offset called the bias. And in this way, we can, by sliding this filter over the input, the result is our convolved feature matrix, representing whatever features that we find important. So all we need to do here is figure out what weights and biases would give us our feature, desired feature matrix. And we do that through machine learning. So we can just see the equation here on the right that just shows we just multiply every element of the input by every element of the filter and sum them all together, as well as add any bias if we specify that. So then if we want to perform classification, what we'll end up with is we'll have what's called a logit for every single class. So we pass this feature matrix to the fully connected layer, and the fully connected layer will map the feature matrix to a logit for each class. This logit basically gives us our confidence in each class relative to every other logit or every other class. So if class 1 has the highest logit, then we might believe that class 1 is the class of our input. So generally here we can perform classification by just finding whichever class is the highest logit. But these logits don't represent the probability of each class. They take the domain, they exist in the domain from -infinity to infinity. So typically we'll apply a softmax layer to these logits, and this will just convert the logits to a probability based on whatever the logit is relative to the other logits in this prediction. We do this so that way we might have a better idea of what our confidence in our prediction is. For example, if we had 4 classes, the logits could be something like 10, so some arbitrary 10 million, 9 million, 9 million, and 9 million. We might think that whatever had 10 million is obviously the class that is predicted. It's the greatest one. But if we convert these over to a probability using softmax, we might find that the first 3 classes have 24% probability and the last class has 28% probability. So we might not actually be that confident that the class with 28% probability is the class that we're predicting. So even though it has the greatest probability, it's not, it really isn't that much more than the rest of the classes. So we use that to kind of determine our confidence in our prediction. And so we can have a better understanding of what we're predicting. So now we kind of know what a CNN looks like, but how do we train these? How would we use these? First, with any design, we want to we want to start by looking at the bigger picture. And in this case, we're going to look at our inputs and our outputs. So we'll define the data and the architecture. So what do our signals look like if we're looking at the signal processing case, or maybe if it's image processing, what do our images look like? Are these color images? Are these black and white images? What features might they have? Are these images of like different animals? If these are signals, are they wireless signals? Are they um, are they maybe some other like audio signals? So the architecture that we choose is going to depend on what we're trying to get out of these. If these are if the data has a lot of complexity to it, if it's very large data or very difficult data to work with, very noisy, we might choose to use a much more complex or a bigger architecture such as GoogleNet or ResNet. But that's if we are valuing our accuracy. If we're valuing inference time or training time and we want some lightweight network, something that doesn't require a lot of processing power or space, we might choose a smaller network and sacrifice our accuracy. So we need to balance all of these things and consider it from a systems point of view first before we actually implement anything. But once we have a design together and we kind of know what we are looking to achieve here and what our inputs and outputs look like, we need to either generate or find a data set. Typically, you'll want to find a data set if it exists first. Why reinvent the wheel if somebody's already made the data set you're looking for and they are allowing you to use it? Then might as well just download and use it. It'll save a lot of time. However, data sets often are unique to each application. This is just a CNN thing, and this is just a common in machine learning. So, and especially in wireless communications where it's easy to synthesize data sets, you might choose to generate or record your own. And you might also choose that if no one has created a data set that fits your specific needs. After you obtain the data set, you need to format it to fit the architecture or whatever you're working with. This could be such as like resizing images so they're all the same, or framing wireless signals so that way you have a standard signal size. So any reformatting data here needs to be done first. And then you're going to want to split it into training, testing, and validation data sets, which I'll get into more in a later slide. After this, you're ready to really start. You can code up your architecture and use this data set to train the network, test it, and finally deploy it. So just an example of what I mean when I say that you have to kind of consider the inputs and outputs. This is a simple one. If you're trying to process complex baseband signals, so you need to consider what these signals look like and what their features might be, depend on what correlation do these features have. So let's assume that we have some wireless signal that we receive. It has, and we're going to group it by every 1024 samples. Well, current implementations of CNNs can't process complex data. They can only process real value data. So we need to consider this limitation when we're designing our system. And the typical way to do this is to split the components into a matrix. So we typically do this by splitting into the in-phase and quadrature components, concatenating them together. So in this example, the first row of the matrix is the in-phase component, and the second row is the quadrature component. You could split them into columns, or you could split them into different channels. In the example, we'll go over the data is split into channels. But either way, we've taken our data and we converted it to something that's a real value, but we still have both components there. And then considering the output types, if you're going to perform regression, which could be either, which you're predicting a real valued number, so maybe predicting the temperature of something, or the power, or the SNR of a signal. Classifying it, where you're applying a label to the input data, like say the color of a vehicle, or in the example we'll go over, the modulation type of the received signal. So with generating a data set, like I said, generally find an existing one first if you can. If not, then it's going to be unique to each situation. So have to consider what your situation requires. For wireless signals, we typically have two different approaches that we've taken. So you can collect the samples from an SDR, but it's generally easier to synthesize the signals using some random input data and applying the desired channel effects in simulation. We often take this approach where we'll just synthesize the data just for training the network, and then we deploy it on an SDR or something, so it's working over the air. It generalizes well to an actual environment. So I kind of briefly spoke about formatting the data set already, but another thing that we need to do is split into three separate sub data sets now. So in machine learning, we have a issue of overfitting. So if our data doesn't represent the general population well, so if we have some subset of data that doesn't generalize that well, we might overfit on it. And this is especially true with CNNs because they generally have much higher complexity than some smaller networks. And so we need to ensure that we're not overfitting, or if we are, we want to know we are, so we don't deploy this network and it ends up failing. And the typical way this is done is to create three subsets from our general data set, our training, which is majority of our data, and then it'll actually be used to train the network, validation and testing. The validation will be used to check for overfitting while the network is training, and then testing is used to just to do a final check for overfitting after the network is finished training. And so essentially here, we're only training on one of these, and the validation and testing data sets are supposed to represent the training data set. But since we're not training on them, we can tell if we're overfitting on this training data set. An important thing here is to remember that you ensure your class balance when you split these. So for example, if you have 4 classes again, and your training data set only has data from 3 of those, when you go to test this, that 4th class is not going to test that well. And you're going to have some large discrepancy in between your training and your testing. So something that happens often and an issue that you might encounter and to avoid. So I'll show a MATLAB modulation classification example. So what you'll need for this is, of course, MATLAB, their communications toolbox. There's a couple add-ons that you'll need depending on what you use for an SDR. If you need 2 different SDRs for this, including at least a add-on Pluto, and then you can also use a USRP, either an N series or a P series, or a second add-on Pluto. I'm going to use a add-on Pluto and a USRP B210. So you'll need the communications toolbox package for both of these if you're going to use them, or if you just use the Plutos, then you just need the communication toolbox for the Plutos. The example is the command to open the example is shown here. So this will be included if you have the deep learning toolbox with MATLAB. And here's a link to the example. Sorry. So I will switch over to the example. Okay, so when you open up the MATLAB example linked in the PowerPoint, you should see a screen like this. So it should open up the directory, and I copied this example to a different folder just so I can modify it without modifying the original example. We're not really going to need to see the workspace variables or anything, so I'm just going to make these a bit smaller to increase the amount of room you have to see this. So this example should be completely standalone other than the equipment needed to test it over the air. You can still train the network and test it in simulation if you don't have an SDR to test it with. So let's go through this one part at a time. So it's going to train on these modulation types. So a couple different digital ones, some analog ones, and they're all also listed here. So let's click on the first section and click run section at the top here. And we're just going to run each section individually. So it first just loaded a pre-trained network. The author trained a network previously. So if you just want to test it, you can just use the pre-trained. We're also going to run through an example where we actually train this network. So the author chose the route of synthesizing samples. And here's kind of their explanation of how they did it. So it's really just starting with a random bit generator and then using a modulator. For this demonstration, they're just using a PAM4 modulator and a square root raised cosine transmit filter, the a Ricean channel, phase and frequency offsets, and clock offsets, and finally just AWGN. So this first part here is just going to generate some PAM samples and classify them with the pre-trained network, just to demonstrate that the network does work. So here's it generating some bits and applying some channel effects to it. Here's all the steps to applying the channel effects, then finally adding the noise. And they use a bunch of helper functions and classes that they created to help organize data and just clean up the example a bit. If you want to see more about how they implement some of these things, such as like some of the channels they did, you just have to right click and open, and it'll open up these. So let's run this, and it'll classify using the classify function on the train net. And this should all classify out as PAM4 frames. And here's the prediction. We can see, yep, all 7 frames that they generated classified correctly as PAM4. And the classification scores for each of these. So if you remember that I talked about the softmax layer gives a probability for each class. And the network is pretty confident that this is PAM4 with a either near or 100% predicted accuracy for PAM4. So next, so that's the train network being demonstrated with some synthesized samples. Next, we're going to actually train our own version of this network. So first, we're going to have to generate all the frames. Typically with deep learning, you need a lot of data. This for other types of learning, you don't necessarily need as much. Still need typically a large amount of data, but for deep learning, you need even more. So there, in this example, we generate 10,000 frames and we use an 80-10-10 split. So 80% of the data is going to be used for training, 10% for validation, and 10% for testing. Additionally, each frame is going to be 1,024 samples. The sample rate is 200 kilohertz. And the center frequency is 902 megahertz for digital and 100 megahertz for analog modulation types. So first, you're going to want to make sure that this dropdown selected for a train network now. If you don't, it's going to generate only 500 samples just for testing. So in here, it'll generate 10,000. So we're just going to run this section just to set those variables. This next section talks about the channel impairments and will set up a channel for us to use. So we're going to use AWGN, Ricean multipath fading, and clock offset. We'll need to run this here, 75 through 77, to set the parameters of the clock offset. If you're interested in the calculations, the math is all here. And the author also created a convenient class that applies all of these channel effects in one function. So you can just specify all of your parameters. So like the path delays and path gains and K factor for the Ricean channel, your maximum Doppler shift, center frequency, all these parameters, and you can change them if you'd like. You can also apply these all yourself. The author shows the effects of all of these individually. And if you right click and open this file, you can see all of the objects they create, as well as how they apply the objects. It's not too complicated if you want to do it yourself. But this, we can also just use this as a simple and clean way of doing it. So running this section creates the channel object. And then this next part will generate the waveforms. So we're just going to default our random seed, so that way it'll produce the same data each time you run this. And it's going to generate the data and save it to a file under the folder frame, or the file's root name will be frame under the data directory specified here. For the example, it's just going to use a temporary directory. I've already run this once, so the data is already generated. When you run this, it might take, depending on your computer, it could take anywhere from 5 minutes to 20 minutes. That takes a decent amount of time to generate all of the data. So I'm going to run this again. If you have to run the data, if you have to run this and are following along in real time, you might want to pause it here and wait until it finishes. In my case, it just says data files exist, skip data generation. In yours, it'll show the each step saying generated BPSK, generated QPSK, all the way up through these. So the next, so it's also going to plot these in the next one. So I'll run this section. And it just plots a brief time series for each modulation type. So we can just see all of these and kind of just eye them to verify if we'd like. And then a spectrogram if we want. I'll run this section as well. You can just see the spectrograms, an example spectrogram from some of the samples we generated. So the next thing we're going to do is actually load this data back into memory. So we saved it to files, and the benefit of this is that you don't need to use as much memory. MATLAB has a library for data stores so that it'll just reference what's on file. If you have the memory available to fit it all in memory, it's a good idea to use that. But in the case these data sets sometimes become too large, they can become multiple gigabytes. So if you're trying to train on something small like a Xilinx system, it might not be possible. Or these things can be tens of gigabytes, hundreds of gigabytes, depending on what you're working with. So a data store is a way just to only load into memory what you need. And this new thing that they've introduced, I don't actually use it much, but it's the signal data store. So it's designed specifically for signals. Previously, they only had image data stores. So this is going to point towards our data directory. We provide the signal variable names, which are just our frames and the labels for each frame, and it'll load them. It'll create an object for it here. And now in order to transform our data to be in the format that we require, remember that the samples, the frames don't just automatically fit into our neural network. For one, we have to separate the in-phase quadrature components. And also we're going to put the in-phase component in the first channel and the quadrature component in the second channel of the image. So we'll apply this transform. This case is just specifying what the transform function is. And now when we run this next section, it's actually going to split them. So this was going to take quite a while. The reason I don't typically use it is because it takes much longer than it needs. It seems MATLAB has some optimization to do on their end. It actually takes so long that the author decided to use parallel pools to evaluate this. And even on my machine here, it took 6 minutes just to load this data and separate it for training, validation, testing. And this is actually, we're going to have to do a few of these steps. So I'm going to go ahead and get this started. So typically I would actually do the separation myself manually, just using a for loop, and then putting the data, like allocating 3 arrays for the training, validation, and testing, and in a for loop, just putting data into each array to separate them. Takes a little while to implement it. You want to be careful that it actually works right. But when you actually go to run it, it only takes it a few seconds to run. So I tend to prefer it. But this example is using the new Signal data store. So we're going to go ahead and use this for now. So for each of these that we have to run, I'm going to pause the recording and resume it when it finishes. So if you're following along in real time, every time I say I'm going to pause it, you might want to just pause this recording, and then when you finish running this step, just resume the recording. So I'm going to go ahead and pause it now. Okay, so this section is finished. Took about 7 minutes to do, but unfortunately, we do still have a couple more to finish. So if we scroll down line 164 and we run this section too, this will have a couple parallel pools, but they're a little bit quicker. This should only take about 3 minutes, 3 to 10 minutes. It looks like this one took 4 minutes to run. So in this case, what we're doing, so the first one is kind of transforming the data set, and it started the split, but it didn't actually perform the split yet. So this is, we're actually going to finish the split here, and we can see that we're creating our RX train frame, RX train frames, RX validation frames, as well as our labels. And we'll create the test ones later. So the train frames are our X data. So this is what we're actually going, these are received wireless signals. This is what we're going to input into the network. And our labels here are the classifications of the, of these signals. So this would be like BPSK, QPSK, whatever the modulation type is of that signal. And so that's our Y. So we're going to use these to train the mapping between X and Y in our CNN. So I'm going to go ahead and pause this again. Okay, so we have all of this generated. We can go through and just see it. Took it probably about 10 minutes to do, 7 to 10 minutes. So now we're ready to go on to training the network. So we have all of our data sets, our sub data sets. Ignore this error here. I was just testing this before. So when we run this, it'll actually create our network, this helper mod class CNN function here. And if we open this up, we can see how that's created. And we'll go through after and actually create our own network. A bit different from this, but we'll see how we actually can construct a network. So I'll close that out and go back to the example. So if you run this, it'll actually create the mod class net here. So this is our actual CNN that we're going to train. So this defines all of the layers and the inputs and outputs. We scroll down. This will specify our options for training. So the maximum number of epochs. When this trains, it'll run through all of the data, and that'll be called one epoch. So it'll train it on the entire data set. Then it'll shuffle all that whole data set and train it again. That'd be a second epoch. In this case, we're telling it to shuffle the data and train it 12 times maximum. The mini batch size. So in order to speed up and improve the training, instead of training on one sample at a time, we're actually going to train on 256 samples of this data set. And generally a good number for this. So these are what are called hyperparameters, and don't have a specific number you should use. It's going to be kind of depend on the situation. For the mini batch size, typically you want to go 64, 128, 256. The limiting factor here is your GPU memory if you're training on a GPU, or your actual system memory if you're training on a CPU, because it needs to be able to load an entire 256 samples into memory. So if you're training with some networks that have much larger samples, then you might be limited on your mini batch size. In this case, 256 should be pretty easy to do. Our samples are not that big. They're just 1024 samples, so 256. We're talking about the kilobytes range. There's other options. Is creating the rest of our hyperparameters. And again, the author decided to create a special function for this. So this is specifying the max epochs here, the mini batch size, the number of labels. So this would be the number of modulation types. And then our validation data set. So let's open this up and see what's inside of it. I'm not sure why that's not opening. So oh, there we go. Just took it a little while. So it just specifies this here. This is just a MATLAB struct for specifying training options. And there are a ton of options that you can specify here. Afterwards, when we modify this example, we're going to re-implement this ourselves. It's pretty simple. We're going to change the training options to maybe something that's a little bit more optimal. We're not going to change much here, but we will see how we can implement this and change it. So again, those are what are called the hyperparameters. They don't actually determine the capabilities of the network, but they do determine how well it'll train. This could mean either training quicker, and in some cases, depending on your options, it can train to a higher accuracy. If your hyperparameters are not optimized that well, then your accuracy might be hindered by that. And there's no one way to choose these. In general, the most popular method for figuring out your hyperparameters is really just guess and check, and knowing from experience kind of the impact some of them will have and what some optimal hyperparameters would be for these situations. There are other types of there's some algorithms for kind of trying to optimize these. Grid search is a popular one. Charles Montes, who should also be recording videos, he is working on some optimization with genetic algorithm to optimize hyperparameters and network architecture. So there's some options out there for optimizing these, but generally, if you could choose them by hand and get decent results. And in this case, we're not going to optimize these because we can get some pretty good results with what's there now. So I don't remember if I ran that. I'm just going to hit run section again, just to create the options. And now I'll click run section in the part below. This is going to call the train network function using our training data, the network we created, and the options that we specified. And so we'll get the training window popping up here in a minute. It's just gathering all the data for us real quick. So this training data window will actually show us the progress of our training. It's still initializing, but this top graph we have here is our accuracy. Bottom graph is our loss. So, and these are by the number of iterations we've trained on. So what we're trying to do here is minimize our loss. By minimizing our loss, we'll maximize our accuracy, but our loss is basically telling us how far away are we from our from being a perfect mapping between X and Y. So In this case, we're using what's called cross entropy loss, which is just your typical loss for classification. If you're doing regression, you might be using something like RMSE. We can see that this is training in the background, and our accuracy is increasing over time. It's going up pretty quickly, actually. And we have some stuff on the right here. So it's going to tell us the current progress. We have a nice progress bar here. And if we ever decide we want to stop it, either because we see an error, or maybe it's trained enough where we think 70% here is good, or it hits like 100% and we see that this still is only halfway finished, we could just click this stop button here and it'll finalize the network for us. So we don't have to sit through this entire thing. But unless we do that, it's actually going to train for the number of epochs we specified. So 12. So, and we can also see here that we'll have 343 iterations per epoch and 4,116 iterations in total. And other things, we can see that it's training on the GPU. Our learning rate is 0.02. So this will take quite a while to train fully. I think the author specified on a Titan GPU, it took him about 50 minutes. So we can just sit tight and do something else while this is running. This is a perfect time to grab a coffee, or if you have other work to do, you can always do that at the same time. So this is something that can just run in the background, but do keep in mind, depending on what you're doing, it can consume a lot of memory, consume a lot of processing power. So running CAD software or something in the background might not be an option. And I've actually crashed simulations or crash training by trying to run other software in the background. So be a little careful with that, depending on the capabilities of your system. I'm going to pause this and come back when it's finished a single iteration. It's currently about a third of the way there, and then show how the validation works. Okay, so this is about to finish up the first epoch. And so what we're going to see here is it's going to reach iteration 343, and it's going to pause for a little bit because it's actually going to take our validation data set and apply it right now. It's going to test the network on our validation data set. And we can see this black dashed line going across both graphs now. That's our validation accuracy and loss. What we want to see here is that the validation closely matches our both curves. And we can actually see it's right on line with the curves. This basically tells us that we're not overfitting right now, that our network is following, it is generalizing well. Remember, we're not training on this validation data set. So the fact that it's able to classify the validation data set tells us that when it encounters other data that it hasn't been trained on, it'll be able to classify that correctly too. This is really dead on with the graph, but sometimes we might see that it's a little bit lower, which is fine. So long as it generally follows that trend. Just know that the validation data set, the validation accuracy is going to be closer to what you're actually going to see than the training accuracy. So if the validation accuracy is high enough for you, then that's good. Sometimes the validation accuracy will be slightly higher, and it really is just the same case that it's overfit a bit, but it just performed a little bit better on the validation set than it did on the training data set. So again, it wouldn't be a big issue if the validation data set is slightly higher than the curve. So I'm going to keep training this for a little bit. If you train it for the entire 12 epochs, you should see that this gets close to 100% accuracy. I'm not going to train it all the way there just for the sake of time, and we can get a demonstration of this working even now we should be able to see 80% accuracy, but I'll let it run for a little bit longer to increase the accuracy a bit. We can see that it's kind of started to teeter off a bit, which is typical. The loss is asymptotically going to go approach zero. And you'll typically find that there is a lowest amount the loss can go, or a highest amount the accuracy can reach. So if you want to see the network trained fully, feel free to run this for all 12 epochs. but you'll get the same results, or you should at least get the same results as the author, and you can just load their network. So I'm, like I said, I'm going to just run this for a little bit longer, maybe another epoch or so. And then I'm going to stop the training and test the network to see if our network overfit or not. So I'll go ahead and pause the recording now, and I'll resume it shortly. Okay, so it's completed another iteration. I mean, another epoch. And it looks like the accuracy might have stayed the same, might have gone up by like 0.01%. This can happen in some epochs. It can actually go down a little bit in some epochs. I've seen it happen like as long as the trend continues to go up, you might see some epochs that are worse than others. But for now, I'm actually going to stop this here. It's trained enough that we can do a demonstration with it, and it doesn't seem to be going up that quickly. So to do that again, I'm going to go to the right here and hit the stop button, and it's going to finalize it, run another validation test. And now it's actually going to run a final validation test and give us our final accuracy. And sometimes this is right on the lines with the previous validation test, but I've also seen the accuracy decrease or increase slightly from this. That's typical too. It usually takes it a minute or two to actually finish this. Okay, so we see the final accuracy is 82.03%. Typically, you're going to want a lot higher than that, but this is fine for a test. I'm going to go ahead and close this window out. You're free to leave it open if you want, makes no difference. And the results are also below here. Here's the results after running it for a long time through from their network. So it seems the results kind of lined up with where they are at. It would have, by the end of that epoch, I guess they were slightly higher, but if you run it for the full time, you should get about 95% accuracy. So this next part is going to collect our test frames. So it's going to use that signal data store again and a parallel pool to collect the frames. I'm going to start that now. So I'm going to hit run section. And then it's going to actually get a prediction. So we're going to use this classify function with our train network and the frames we want to classify. So this is actually going to perform inference, and you can use this in deployment as well, this same function. And then they're going to calculate the accuracy by comparing the test prediction with the actual true labels and display that. So this is going to take a minute again. I'm going to pause the recording again and come back when this finishes. Okay, so it's finished up. Only took it a minute, and we can see our test accuracy here is 82%, which is right in line with what we were seeing. I think our accuracy above was, 82.03% for our validation and 82.03% here. So it's pretty much right on the money. We can see that there's no overfitting going on here at least. So in the next section, it's going to create a Confucian matrix. So the Confucian matrix is going to tell us when things misclassify, which classes did they misclassify in? So in other words, here we can see that for most of the classes here, like 8PSK, almost all of the 1,000 samples were correctly classified as 8PSK. So here's the true class. And for the true class, we predicted 962 of those as 8PSK. And some of them misclassified as 16 QAM and QPSK, but no real trend there. So it worked out pretty well. If we go to QPSK, though, we can see that almost no QPSK samples were classified correctly. So there's where all of our accuracy went. So if we train for a while longer, that might have worked itself out. So it just probably didn't get to train correctly on QPSK yet. We can see that those were all 8 PSK, which makes sense. If it was going to be mistaken for a modulation type, 8 PSK would probably be the closest to QPSK. And the other ones at fault, we have a little bit of them in DSB AM, which were misclassified as SSB AM, makes sense. And then if we look at 16 QAM and 64 QAM, those two classes were mixed up quite a bit. So this confusion matrix can be very useful for telling, for diagnosing your network to see where classification might have gone wrong and how to improve it. In our case, this probably would have just been improved by training longer. I believe the authors, they did not include their own, but if you loaded the test network in again and reuse that, you should see a confusion matrix that is pretty much perfect, or at least 95% accuracy. So the final test we're going to do here is with an SDR. So for this, the authors used a add-on Pluto as the transmitter. It also gives you the option of using another Pluto or a USRP as the receiver. In reality, you could do both of them on the Pluto. The Pluto has the ability to use transmit or to load some samples onto the FPGA and play those on loop on the transmitter. Not sure why the author didn't go with that. It would have, as well as if you use a B210, you can use both the transmitter and receiver in that. But we won't modify that now. If you only have one of them, the modification for Pluto would be pretty simple, but is more of an SDR thing than a CNN tutorial. So I won't really go into that. So this is going to, this code down here is basically going to detect what platforms you have, or detect the radios based on the platforms you choose. So it's first going to detect the Plutos for transmitting. And you can select the radio platform that you want to use up here. I have a Pluto and a B210, so I'm going to select B210 for the receiver. And I'm going to hit run section. As it goes through here, it's going to find all the connected USRPs. And since I said B210, it's only going to look at those radios that are a B210. So this does take a little bit for it to find the USRPs. This find SDRU function's a little slow. Okay, so now it's going through and actually testing. And if I look at my radios, I can see the B210 has an LED showing if it's transmitting or receiving or doing nothing. So I can see that it is receiving occasionally, and the Pluto is transmitting. And we can also see an output down here, so that it found the TX radio as our Pluto and our B210 here. And so it finished, so it just transmitted BPSK frames, so testing BPSK frames first. And then after this releasing TX radio, we can see the test accuracy was 95%. And let's scroll up to our confusion matrix to check real quick. And it's slightly lower than our test accuracy, but right along the lines, that's 99%. We had 95% over the air. We expect to see QPSK much lower, and testing QPSK frames, 47.5%, APSK 62%. So it's in line with what we expect. So I'm going to pause this while it runs through. It should only take it a minute, but if you're running through it now, you might want to pause the recording. Okay, so this is finished up now. Scroll down. Unfortunately, I don't think it's going to show me all the individual accuracies here. That text is cut off, but we can see the confusion matrix generated. And it pretty closely aligns with what we were seeing before. So it didn't test the some of the analog modulation types. I believe that is just because the Pluto uh, can't transmit on that center frequency. So the author decided not to use them. But we can see the same patterns as before of QPSK and 8PSK being mixed up, and 64 QAM and 16 QAM being mixed up. So let's just double check that with ours. And yep, we see the same things happening with 16 QAM having a little bit higher accuracy. So we can verify that our network, even though we trained it on synthesized samples, was able to generalize very well over the air. And if we trained it longer, it would be able to classify these other classes very well. So that's it for the base example. Let's look at modifying this a little bit. So the first thing we're going to do here is actually implement our own network. So it's going to be a little bit different than what the authors implemented. We're going to make use of something called Stride. I briefly talked about it in the presentation, but Stride basically makes the our filters move a little bit further. Instead of just moving by one, they'll move by whatever we specify. So we'll tell them to move by two. And this means that every time we every feature extraction layer will have the amount of data. So we will significantly reduce the amount of data by the time we get to classification. This will make it train faster, but it can also sacrifice accuracy, as we'll see. So let's scroll way up to line, let's be like 150 or something. I think I went too far. Line 176, where we define mod class net. So I'm going to comment this out, just using a percentage sign in MATLAB to comment things out. And we're going to define it ourselves. So we'll say mod class net equals, and then open square bracket. And we'll define each layer on a line. So the first thing we're going to need is our input layer. Depending on what you're doing, this is going to change. What we're going to use is an image input layer. So an image input just basically says we're going to specify a matrix. They say image, but it means matrix. Say image input layer. And then as an array, we'll specify the size. So it's going to be 1 by our samples per frame, SPF, or 1024. You could also say that, by 2. So remember, we're going to have our in-phase component as the first row. And then in the second channel, we'll have our quadrature component as a row. Then on another line, we'll go 2 lines down and we'll specify our first convolution layer. So we'll say convolution 2D layer. The D is not capitalized. And then in square brackets as an array, we'll specify our filter size. And we're going to specify the filter size to be the size of the samples per symbol. So we're basically saying the samples between the samples that contain each symbol are kind of extra, and our feature size is spaced by each symbol, which makes sense if we think about the difference between like 16 QAM and 64 QAM. The differences in the way we modulate the symbols. The pole shaping is the same, at least in this example, our pole shaping is the same for them. So we'll say 1, comma SPS, samples per symbol. And then outside of those square brackets, we're going to specify the number of filters. So this won't actually apply just one filter for this convolution layer. We get to specify the number of filters we're going to use, and we're going to use 16 here. So this is going to be 16 independent filters that are going to be applied to our input to give us 16 feature matrices as our output. Increasing the number of filters here increases the complexity, allows us to work with more complex data, model more complex functions, but it will increase training time, and it also can increase your chance of overfitting. The next layer we'll use is batch normalization. So batch normalization layer. And I won't get into much detail about this, but the goal here is just to reduce internal covariate shift between the layers. Essentially, back propagation might change the way that the input, what the input looks like between these layers. So when we try to train this convolution 2D layer, we're training it based on the next layer, and the next layer is trained first. So we're always trying to change it on a moving target, and it makes training a little bit difficult. So these batch normalization layers help to normalize the what the data looks like between the layers to try to reduce this. We're going to add some activation, and we're going to add rectified linear unit, or ReLU. This is simply just if the output is below zero, if the input's below zero, the output is zero. If the input is above zero, we pass it. So just kind of like a gating function. We just pass anything that's above zero. And then a max pooling layer. So max pooling 2D, lowercase d layer. And then we need to specify in square brackets as an array, the pooling size. So just like our filter size for a convolution layer. And I will use, sorry, a 1x4, a 1x4 pooling size. Then we're going to specify another option, or stride. So we'll do comma, and then as a string, stride, and then another array specifying how much we will stride by. And in this case, we'll do 2x2. We could say 1x2 here because the data is only a vector. So now these filter sizes and these pooling sizes are important. They can't be greater than our data size. So if we try to say a convolutional filter size here of 2 by SPS, we're going to have an error. That's because our data is only one row, one row long. And so if we tried to have a filter size that's 2 rows long, it's not going to be able to apply. We're going to have some issues there. And MATLAB will give you an error for this, so you won't even be able to train with it. Similarly, whenever you have these convolution layers and these pooling layers, even without stride, they're going to reduce the data dimensions, which is what we want. The feature matrices should be smaller. So you're limited if you keep applying these convolution layers. You have to keep in mind what your data size is. So in this case here, we're going to remove 8 samples from the end of it with this convolution layer. And then this pooling layer is going to remove 4 samples, as well as have it because our stride is 2. And we'll see after how we can actually visualize this network and just verify that we are within the dimensions that we should be. So let's repeat this 3 times. So that way we have 3 series of convolution or 3 feature extraction series, which is a small amount. Typically you might have more. So I just copied this and pasted it 3 times. So we have the same thing. And we'll go through and modify these. So on the second convolution 2D layer, let's change the number of filters to be 24. So it's increasing the number of filters, increasing our complexity. On the third convolution layer, let's increase this to be 48. We're also going to change this max pooling to average pooling. The difference between max pooling will basically in a 1x4 area choose the feature that has the highest number of or the highest value. Average is going to take all 4 of these features and average them together. Max pooling is much more popular to use, and average pooling is sometimes used as the last pooling layer. There's no rule here. You might want to experiment and find what works best for you. So that's the end of our feature extraction. Now we need to add the classification stages. So we'll start with a fully connected layer. So it's a fully connected layer. And we need to specify the number of logits, or in this case, the number of classes. And our number of classes is 11, or also stored in non-modulation types. And so this will automatically convert. This layer will automatically flatten the output of the previous layer and then map it to 11 logits using a fully connected layer. In order to get our probabilities, we need a softmax layer. We can just specify it as that. And lastly, we need some output. A softmax layer isn't an output in MATLAB. In other deep learning frameworks like TensorFlow, you could just use any of those as an output. But for MATLAB, we need some output layer specifically. So we want classification. We'll just say classification layer. And this will give us a label output instead of a probability. And with that, our network is built. So we can hit run section now. And it looks like it's taking in a minute, but here we go. So we have our array, and that's our network. That's all we need. So let's expand on these a little bit. So I'm going to scroll, just drag this command window open, and let's look at our first convolution layer. So if I address this as an array, the convolution layer is the second element. And we can see our weights and biases here. We can see a bunch of options here, our filter size, and our weights and biases are empty because we haven't initialized this network. When we go to train it, it's going to first initialize it. It's going to give us some random weights and biases and then train them. So after we train, we can come back and look at these weights and biases and see what it's updated them as. We can also visualize this network using the analyze network function. So I'm going to type that into the command window. So analyze network, and I'll type in mod class net. So this is basically going to show us what the inputs and outputs of every layer is, and maybe some other information if we're interested in seeing it. So I'll hit enter. It'll take it a minute to generate, but a window will pop up. And I'll just full screen this. On the left here, we can see the visualization of the network. Since our network is just a very straightforward linear network, it's pretty simple. But if you have a more complicated network like ResNet or GoogleNet, this can be a lot more much more useful. So what we can see here, what's the most important thing to see, we have no errors. So that's great. No errors and no warnings. If you had that issue I was talking about where your data dimensions became too small and too small for the next layer, it would show up as an error here. And we can actually see the output dimensions of everything. So our output dimension of our activations is 1 by 1024 by 2, what we would expect. That's our input. Our output of our image input is that. That's the input frame. After our first convolution layer, we take away 8 from that. And we also have, remember, we have 16 filters. So we're going to have 16 feature matrices as our output. Batch normalization and ReLU don't reduce data dimensions, but max pooling does. And we can see that we've taken away 8 and then halved it. So we have approximately half of our original input. Sorry, we're taking away the filter size -1, so we take away 7. And in this case, we take away 4 and then half it. Or, sorry, 3 for the pooling and half it. So if we then look at continue down this, we can see our data dimensions continuing to decrease in our activations until after our average pooling, we have our 48 feature matrices that we specified. and each of them is 1 by 120. The fully connected layer, we can see that we flattened this and converted it to 11 logits. So 1 by 1 by 11. So just a 1 by 11 vector. And the same thing, softmax is keeping the data dimensions because it's just converting them to probabilities. So I'm going to close this out. We don't need this for training. It just visualizes the network. I'm going to run the next sections again. We shouldn't need to run these, but just to make sure we reset anything that might be needed. So the next section would be line 199, and I just hit run section at the top. This might be taking a little while because I've loaded a lot of data into memory. So finally, we'll run the training again and see the difference. So I'll start before I run this. Let's just review the way our training, what happened the last time. So we ran about 2.5 epochs, maybe 2 1/3, and it took 18 minutes for that. So maybe roughly about 7 minutes an epoch. 5 to 7 minutes at epoch. And after the first, very quickly, it actually reached around 80% accuracy, around 100 iterations. So we should see this train much quicker. First off, our network is far less complex than the one that's given in the example. And it's also, because it's less complex, we should see it train a lot quicker. It shouldn't train to as high of an accuracy, but it should train quicker. So I'm going to hit run section, and we'll have that same training window pop up. So it's just take a minute for it to load all the data. Now we can see, yeah, it's training far quicker. We can see this is already on epoch iteration 100. And it's about to finish up the first epoch in about 30 seconds. So 7 minutes down to 30 seconds. We've increased the training or decreased the training time significantly. But because the network is smaller, we probably won't see the same level of accuracy. I'm going to go ahead and pause the recording now and resume it once it finishes training. All right, so our training's finished. And it looks like it's just shy of 95%. So with these modifications, we were able to train in less than 1/3 of the time that our first trial went. And that only finished 2 epochs. It didn't even finish the third. So smaller network with some stride really seemed to improve this by a lot. And if we train it for longer, we might even be able to get some higher accuracy, but that's probably unnecessary for this. It's probably limited by its low complexity. So 93.5%. I would say that's fine. And like I said, it trained a lot faster. So it's just some optimizations to your architecture can make a huge difference. So I'm going to close that out. We can see that here. So it has a very similar training curve, accuracy curve to ours, theirs versus ours, but ours trained in much less time. So let's go ahead and run a test of this and just see how it performs in the test. And since this is going to require running the parallel pool again and all of that long stuff, I'm just going to pause briefly. Okay, so we've run our test and we get exactly what we got in our validation accuracy, 93.55%. So we can see that we didn't overfit despite our network being a bit shallow. I'm not going to test this on the SDR. You can test that if you want, but we've already run the other example on that. The last modification we're going to do to this is to change the hyperparameters, or the training options specifically. We're not going to use their training options, helper mod class training options file they created. We're going to implement them ourselves. So let's see. Okay, right here. So line 201 and also 202, we're going to comment those out. We're not going to use those. Instead, we're going to specify the training options ourselves. So sorry about that. So I'm just looking at the MATLAB wiki right now, or their API docs, looking at the function training options. So the first thing that we'll do is this. So these have, this has quite a bit of options here. So you probably want to reference the documentation on this training options here, just to see all of the different things you can specify. We're going to look at a few of them, definitely not all of them, because most of the defaults are actually really good. So the first thing is the original example used SGDM, or stochastic gradient descent with momentum. It's a good optimizer, but it is a bit old. There's been newer, more and some more popular ones now. And those include RMS prop and Atom. I'm just looking at the documentation to see what MATLAB supports. So we're going to use Atom. So we use solver name as a string, and then Atom. So each of these options, we're going to start with a some key here to identify the option we're going to change. And then we're going to specify, say comma, and the option, whatever we're going to provide as an option. Final comma, and then dot, 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 just to say we're going to the next line. Some weird requirement in MATLAB. So we'll need, next is our initial learning rate. And we'll just say 0.02. Our maximum number of epochs. We can leave this as it was, that worked fine, but here you can specify if you wanted 25, 100, 1, whatever you want. Mini batch size. So again, the training algorithm is going to separate our samples rather than just train them one at a time or train on every sample at once. It's going to batch them into mini batches. So we specified 256 of them. We're going to train it on 256 samples at once. We wanted to shuffle the data every epoch, so we're going to specify that here. So we'll say shuffle and then every epoch. We can choose whether or not we want it to actually plot anything. We don't have to have that training plot, but we want it. So we do need to specify it if we want it. So we're just going to say plots and then training dash progress. Additionally, you can have it output to the console through verbose. So this verbose parameter. We didn't have that enabled before. Generally, the training plot is my preferred way of doing it, but if you want to document it, say save it in a file for later, the training plot doesn't save that well. So you might want to use verbose for that, because you could just copy the console output and put it in like a Word doc or something for documentation. So we're just going to put it on as true just to see what it looks like. And I don't typically use it. If we want to use validation, we specify the validation data here. And we specify this as a cell array. So that's going to be curly braces. So our validation data is Rx valid frames, or X, and then Rx valid labels, or Y. both inside the curly braces. And then comma, next line. Our validation frequency, how often we should validate. And this is in the number of iterations. So we'll actually have to calculate this out. So for now, we'll just use a variable, a temporary variable validation frequency. We haven't defined this yet. After we finish typing out these options, I'll go ahead and define it above and show how we can calculate out the number of iterations per epoch. Our learning rate schedule is the next thing. So this is going to, actually, we won't be specifying this because we're not using SGDM. This is, if we wanted to drop our learning rate as our training goes on, we can do that. So the learning rate in any solver here, by having a larger learning rate, we can learn quicker, but we might not be able to reach a minimum. Dropping, so if we use a lower learning rate, we could get stuck in noise, or we could just take forever to actually learn. But if our learning rate is too high, we'll never get to a minimum. So there's a trade-off there. And typically with SGDM, what you would do is you would train until you see that you've your loss has hit its minimum, you're stuck in some minimum, and then you would drop the learning rate so that way you can get the even further down in that minimum. The benefit of these newer solvers is they actually try to do this. They try to learn these parameters as it goes. And, they try to optimize this. So Atom will actually change the learning rate as it goes on. So it'll increase it if it needs to, or decrease it. So we don't actually have to specify this. I'm going to erase this line. We still need that ... on the end, but no final comma here. So there shouldn't be a comma after validation frequency. So there are options. Again, we just have to calculate out our validation frequency. So this is, again, the number of iterations. How many iterations should we wait until we validate? And we want it to validate every epoch. So let's calculate that out. So this is simply the number of training samples divided by our mini batch size. So this is the number of mini batches per epoch. So if you wanted this to be every 2 epochs, you would just multiply this by 2. Or if you want it to be every half epoch, divide it by 2. But it does have to be an integer. So let's run this, see if we had any errors typing it in. It is taking a minute, probably because it has to load these data sets. MATLAB's going to verify that these data sets do satisfy the inputs and outputs of this network. For example, it's going to check that this is a 1 by 1024 by 2 input dimension, and that there are 11 classes in your labels. Should be any moment now it finishes. Well, it's taking a little bit for some reason, so I'm just going to pause for a moment while it figures out what it needs to do. Okay, so it was taking a while because we actually don't have one of these variables defined. This is actually supposed to be the number of elements in our training array. So we can just do num elements, num-l, rx train labels, and this will just tell us the number of training samples we have, and now it should evaluate correctly. Invalid solver. Okay, so something Not sure why that's throwing an error. That's exactly as they type it in that is exactly how they type it in MATLAB. When I'm looking at their example documentations, let me pause just to figure out why it's throwing that error. Okay, so for some reason it doesn't want us to use solver name first. I'm not sure why, because, well, that's the parameter that it specifies it as in their documentation. But if you just previously, it looked like this. So just if you remove that solver name key and just say Atom as the very first parameter, it'll run just fine. All right, now we can train it. I don't expect to see drastically different parameters here. It actually trained very quickly, quite well. But we might see it train to a higher accuracy in the end. So remember, we had 93.55% as our final accuracy. So let's see if maybe we can squeeze out a little bit more accuracy from this. So it actually looks like it's training a little bit slower in the start. We'll see as it goes on. I'm going to pause this and see, actually real quick first, just to show that we did our calculations right. The iterations per epochs 343. It's about to finish that. So let's see, after 343 iterations, we should see a validation. And there we go, right about on the edge there. It might not be perfect because we did round it. We did floor that calculation, so it could be calculating as 342 or 344, but it's every epoch it's validating it. So yeah, I'm going to go ahead and just pause this and resume it once it finishes. All right, so it's finished up, and we can actually see it trained to a slightly lower accuracy, 90.45%. I've also noticed that it did take a little bit longer to run. So I think MATLAB might be running into some memory leaks or something here. Something's bogging it down. Even though it's the exact same data, it took a little bit longer to train. Not really sure what's going on there. It could be that the optimizer takes slightly longer every iteration. In this case, the Atom optimizer probably doesn't make a huge difference, but when you have much larger data, much larger networks too, with higher complexity, that's when you might really see it shine, when the hyperparameters are difficult to tune. So this has been a brief example on using CNNs for modulation classification in MATLAB. I hope you've learned something from it or it's been helpful. If you have any questions, please feel free to contact me. Contact Dr. Joe, me through Dr. Joe. And yeah, thank you for listening.